Okay, I'm going to walk you guys briefly through chapter 3 and 4, just kind of briefly here, just functions. A function is a rule that assigns exactly one output for each and every input. All your inputs, the set of all inputs are your domains, the set of all outputs are your y's, your range. Your domain is all your x's, your range is all your y's. All your inputs are your domain, and all your outputs are your range. So here, 2, 3, 1, 4, negative 5, 0, negative 9 for x. Y is 5, negative 1, 3, negative 2, 5, 6, and negative 1. Is a function because every x has a y, and no x goes to a different y other than one value. So the domain is all the x that you see lined up here in order, the way I wrote them. The range, notice, is 5, negative 1, 3, negative 2, 6. Negative 1 and 5 repeat themselves. You don't write them again. This one's not a function because 4 cheats. He goes to 5 over here, and he goes to negative 6 over here. So you can say no x can have more than one y. So in this case, 4, this x cheats and has 2 outputs. So that can't be a function. Linear functions essentially just are like they're lines. The function y equals 2x plus 3, essentially just plug in some x values into the function, get y values back, and you plot essentially points and you get a line. It's not that bad. It starts here at 0, 3. Then you can plot these other points and you're going to kind of see the line go upward here. Y equals mx plus b is essentially a linear function where if it's positive, the slope goes upward. If it's a negative slope, it goes downward. Here I wrote a few points so you can kind of plot them on your own. I just kind of plotted one point, which is the y-intercept. The domain is negative infinity to infinity, and so is the range. All real values of x and all real values of y. All real values of x for the domain. In other words, you can plug anything you want for x and get an answer for y. And every time you plug in a value for x, you're only going to get one answer for y. So all lines are linear functions. The domain is negative infinity to infinity, and so on. This just gives you a sketch of what that one is. So just lines. Now, essentially, what does it mean not to be a function in a graph? In a graph, put this thing sideways so you can see it here. Use a vertical line test. If you run any line through here, through the picture, and any vertical line hits the graph at more than one point, it's not a function. So B and D would not be functions. A and C would be. The domain for A would be 0 to infinity all the way to the right and 0 all the way up. The domain for the left, negative infinity to for letter C, negative infinity to infinity. The range is the y value, so 0 up. These two are not functions, so I didn't put domain and range there. Just a little introduction to what essentially a function is and the different kinds of functions here, or some of the different kinds of functions. A piecewise function says, under certain circumstances, if x is a certain value, then it's a certain equation that goes to x. If it's a different value of x, you have a different equation. So what I did here very simply was kind of plug in some values for x. And so if I pick 0, 1, and 2, I'm putting into the first formula. If I'm putting the numbers 3 and 4, I'm putting into the second formula, showing you how the second formula would be this part, the first formula would be that part. But the graph together is what to call a piecewise function. So it's defined a piece at a time. Same thing over here. If it's less than or equal to 1, you get a parabola. So you get a parabolic function. If it's x minus 1, when it's greater than 1, this is a radical function, and it goes up and to the right. That's essentially like a college algebra idea. And so the domain is still everything from left to right, and the range is from 0 up. This one, the domain is everything from left to right. The range is from 0 up to, 0, negative infinity up to 3. Now, applications, linear functions, they have some applications in business, and I'm not going to look at anything too fancy, but in chapter 3, section 3, talking about revenue. Revenue is essentially how much you sell each item for and how many items you sell. The price per item times the number of items. The cost you to make it is some kind of fixed cost at the beginning plus some kind of variable cost. Now, this variable cost essentially would be how many you make times how much it costs to make each one. The profit is the revenue minus the cost. X is the number of items. the cost would be some mx plus b or some b plus mx. So the b is a fixed cost, the mx is your variable cost, the m is your slope, it's the price per unit. And then m is also called marginal cost. It's the cost to make it's the cost per item. So it's called marginal cost. And now C of x is the cost, P of x is profit, R of x is revenue. So P of x is R of x minus C of x. How much you make profit is how much you make minus how much you spend. This kind of makes sense. The average cost is essentially how much it costs to make that number of items times essentially the number of items. So how much does it cost to make all those items divided by how many items you're making? That's how much essentially it's going to cost to make you average cost of one. Break even is when the revenue and the cost are equal. That's when you break even, when you spend as much as you make, or when you make no profit. So either way, just a couple of formulas there. And when the revenue equals the cost, there is essentially there is zero. So it kind of goes hand in hand. So I just worked out a couple of small problems here. A company manufactures TVs to sell for $550 each. The cost of making X number of TVs for a month is given by the cost function C of X equals 250X plus 210,000. Now 250 is the cost per TV, X is the number of TVs. 210,000 for some reason is like some kind of fixed cost. The revenue function, therefore, is if you're going to sell it for $550 each, and you're going to sell X number of them, the revenue cost me 550X. What's the revenue of selling 100 TVs? Well, you just plug in 100 into part A, and that's when X is 100. That tells you how much to make 100 TVs. What is the profit function? Well, it's the revenue function minus the cost function. And so you subtract and you distribute the negative combined like terms. There is your profit function. What is the break-even point? Well, you break even when this is zero, when the profit is nothing. So you finally break even when you sell 700 TVs. So you got to sell 700 TVs just to break even. But once you pass 700, hopefully, you're going to have some good profit. The total cost of producing number of college books is C of X equals 42.5X plus 80,000. What are the fixed costs? The fixed cost is the 80,000, the B. When X is zero, essentially, the B part. What is the marginal cost? It's the slope, the M, 42.50 or $42.50. What is the cost of producing 100 college algebra books? 1,000 college algebra books, you plug in 1,000 into this function for X, you get $122,500. That's a lot of money to produce 1,000 college books. What is the average cost? You take that cost to make 1,000 of them divided by the 1,000 that you're making, and it costs you about $122.50 to make each book. And that's why they sell it to you for $200-300 nowadays, just theoretically speaking. Quadratic functions, these guys are defined as parabolas, happy face or sad face. They have two types of equations. They have one with no parentheses and they have one with the parentheses. The vertex is defined to be h and k, or the value hk. The vertex is the maximum value if it opens down when the a value is negative. The vertex is the lowest point when it's facing upward or when the a is positive. Again, you can go back and review this. You kind of look over the good thing about the video is you can pause it and kind of go back and watch it again. So when it's the first equation, the vertex is h and k, but the h value is negative b over 2a. It's a little formula. You can keep this little formula here. And the k value is f of h. It's the function this value plugged into the function. So for f of x equals negative 2x squared plus 8x plus 3, b is 8 and a is negative 2. So it means a is negative, so it opens downward. So negative of b, negative of 8, divided by 2 times negative 2, which is your a value. So negative 8 over negative 4 is positive 2. To find the k value, plug in 2 into the function, you get 11. So the vertex at 211, and this thing goes down. If you want to find the x and y intercepts, you can. But for me, I just want to kind of show you how to just graph this a sketch. Over here, same type of thing. A is 3, except it's going to open up now. B is 24. So negative of b, negative of 24 divided by 2 times a, which is 3. So negative 24 over 6 is negative 4. When you plug in negative 4 into the function, you get k value to be negative 8. So I went to the point negative 4, negative 8, just roughly here, just schematically, I just guesstimated. I didn't count by ones up here to get 11. I didn't count by 8 by 1 to get to negative 8, and so on. Just kind of ballparked it, and that's your graph. Your domain is negative infinity to infinity. Your range is from negative 8 up. Here, your range is from negative infinity up to 11. The range is everything because it opens forever. Now with the parentheses, a little easier because it opens downward here because a is negative. The opposite sign of -1 is +1. This is +4. So opposite, same. Same thing over here. Opposite, same. There's your vertex. So go to that point and draw this guy going down. Go to this point and draw this guy going up. Essentially, that's all it is. And the domain of all the quadratic functions, -infinity to infinity. The range depends if it's going up or down. If it's going up, essentially it's going to be from that number up to infinity. If it's going down, it's from -infinity up to that number. So it just depends. 3.5, you talk about polynomials, which are powers of x's. So here I just kind of put parentheses. Now, you can have you're going to have tails that either go up or down, and you're going to have behavior at x-intercepts, whether they're bouncing or crossing. Now, to find x-intercepts, you let the function be 0, and you set each of these equal to 0, and you solve. Now, because these are one parenthesis of each, if it's an odd number of parentheses, it's going to cross. If it's an even power or even number of parentheses, it's going to bounce. So that's what tells you it's going to bounce across. So here, they're all going to cross at those numbers. So now, you see this leftmost intercept, this -1? Pick a number to the left, say -2. Plug -2 into the function. If you get a y value of negative, then the left tail is down here. If it's positive, it'll be up here. So because the left tail is negative, you start at the bottom, then you're going to cross it all three, and you're going to end up going up to the right. Essentially how it works. Now, usually if it's three of them, it's third power x to the third. So you plug in a -1 or a +1 and kind of see what happens. But I'm doing it this way. So here, set them each equal to 0, you get the answer. You get x equals 0, x equals -3, x equals 4. Because the 0 came from x squared, that's an even number. So even number is like it's like your parabola. It does some kind of bouncing effect. So if it's even power, it's going to bounce. If it's an odd power, which here are ones, it's going to cross. So crossing, crossing, bounce. To figure out how the tails look, take your leftmost x-intercept. Pick a number to the left. Say -4. Plug in -4. If you get a positive number, the tail is above. If you get a negative number, the tail is under. Because here we get 364, it's above. We're going to go from the top, then we're going to cross at -3. Then we're going to have to turn around some amount. I don't know how much. We're going to have to come back to 0, where we're going to bounce. We're going to have to go down some amount, but eventually come back up to 4, and we're going to cross at 4. And essentially, that's how the graphs look. Just rough guess, just a rough estimate, essentially how just a rough sketch, essentially of how chapter 3 goes. And so, I guess rather than stop the video here, I have some information from chapter 4, and since the first test covers chapter 4, it would probably be easier if I just kind of continued with chapter 4. So I'm going to keep this brief. I'm going to talk to you about an exponential function. It's a number raised to a power, a base raised to a power, a to the x, where the base is greater than 0 and it's not equal to 1. The power is your x, that's your variable. So if the base is bigger than 1, this thing is an increasing function, because anytime you multiply a number over and over and over, it's going to get bigger and bigger if that number is bigger than 1 to start. So this number, this base, has to be positive. It has to be not equal to 1, essentially. And so if the x, as the x grows, so does the y. So does the y value. So does the graph. Now, if this base is less, think of multiplying a small number, like half of a half of a half of a half. Eventually, the number is going to shrink. So if the base is less than 1, this thing's going to decrease. If it's greater than 1, it's going to increase. So like 2 to the x, upward, like this fashion. 2/3 to the x will go down. E to the x, e is understood to be 2.718, that's in your calculator. That essentially is how it works. Just to kind of give you an idea, I'm going to talk to you briefly about exponential growth. As you talk about exponential growth, if the value you're talking about here, if the k value is greater than 0, if it's positive, this is going to be essentially the same thing as an increasing function. If the k value is less than 0, you have decay, so you have going downward. So here is y0, which is y0, y sub 0. E is the value 2.718. It's just exponential growth. It's Euler's number. You can take a number to a power, you can take e to a power. You can take some base to a power or e to a power, where the base is bigger than 1, essentially, and the value is, if the k value is positive or not. It just depends. So now, briefly here, if I may. The amount of debt across all sectors in billions of dollars is approximated by the function f of t equals 1946 times e raised to the 0.083 t, where t is time in years and t equals 0 corresponds to the year 1970. What was the original debt in 1970? So in 1970, the debt was when time was 0. That's the initial time. So you plug in a 0, that's 1. So initially, you're at 1946. So the first one, the y sub 0, that's your initial. So that's what it basically wants you to understand. The original debt is the original problem. So 1,946 billion. What is the debt in the year 2000? Well, 1970 is 0. 2000 minus 1970 is 30. So the idea is approximate, plug it in here, putting the 30 in. So if I may, see if you can see it here. 1946 times, and I have in mine, I have a second and an ln button. The E button right there, and 0.083, if I have that right, 0.083 times 10. That's not right, times 30, excuse me, times 30. And that's where $23,471.24 billion. That's all it is, just to get your feet wet a little bit, just to try a couple application problems. Nothing fancy, just to kind of walk you through this. Then you have logarithms. A logarithm is kind of like the inverse. It's the inverse of an exponent. It's kind of like the opposite of an exponent. So essentially, log base a. That's a log base a of x. Now, this guy goes upward if the base is positive. This guy goes downward if the base is negative. Now, if I may here, and I probably should have done this. Let's see if I can find this here. Second e. Kind of so you can see it a little bit. E to the x. There's your increase. Now, if you do y equals, let's say 0.5 raised to the x. See, it kind of goes downward. So if it's less than 1, so I can actually go over here and I can clear that one. And so you can just see the downward one. Now, if I put y equals log of x, and I realize that it doesn't have a little base, but a logarithm with no base is understood to be 10. So if I may here, let's see if I can, should come from the bottom. Yeah, I didn't put enough here, so let's see. The window, let's say, what? X is minimum 6, let's say x is minimum -1. Max is, I guess that 10 is fine. Log base 10 of 100 is 2. So let me go 100. Let's see if that changes anything. No, that makes it worse. Okay. Let's see actually the max minimum should be, let's say 0.5. Let's jump by 10. Let's say the minimum is negative 20 to positive 40. See how that works. No, it's not enough. I guess I have to play with this a little bit longer, but I just wanted you to see how this works here. I need to. Just give me a second here. I guess that might be a little better. Kind of like this. The other graph is the 0.5 x. I can do 5 raised to the x. So you can kind of see them together. Logarithm starts from the bottom, goes up. The other guy starts from the bottom. This guy goes like this. So they're inverse of each other. Essentially, what they are. So let me get out of that screen here. Okay, so logarithms go up from the bottom if its base is bigger than 1, it increases. If it's less than 1, it goes downward. So if it's base of 3, it goes up. If it's base of 1/2. If it's natural log is essentially the E button. So if I may here is natural log. If I do natural log of E, you see the ln and the E cancel and I get a 1. So natural log is really base E. They're inverse of each other. They cancel each other out. That's what they do. So if you take essentially what does a logarithm mean? It means if you take y equals log base a of x, it means a to the y equals x. Basically means like this. If you take log base 2 of 8, it means 2 raised to what power is 8. So log base 2 of 8 is 3 because 2 to the third power. It's the missing power. Log base 3 of 81 would mean 3 raised to what power is 81? Well, 3 to the fourth is 81. So log 3 of 81 is 4. And so there's a change of base formula that you can take natural log essentially of any number of this number out here divided by the natural log of this number, assuming that they're all positive numbers that you're taking the logarithm of, because you can never take the logarithm of negatives. So if you take natural log of 200 divided by natural log of 5, essentially that is, let's see here, log of 200 natural log of, well, I guess that's wrong here then, because change of base will be log base 5 of 200, natural log of 200 divided by the natural log of 5. So that essentially will be 3.292. Sorry about that. That's why you don't want to use too much pen, but I've been using pen here. So log base 7 of 1/5 will be natural log of 1/5 divided, again, it's natural log of the number that you're taking the logarithm of divided by natural log of the base. So ln of 1 divided by 5 divided by ln of 7. Jeez. Oh, sorry, I put 2 parentheses here. Give me a second. Natural log of 1 divided by 5 divided by natural log of 7. Sorry about that. I put the extra parentheses, kind of messed up the problem there. I was like, man, I messed up twice. I didn't want to do that, but yeah, there's your natural log. Now, if you take the natural log of 1, ln of 1 is always 0. Natural log of 1 is real nice. It's always 0. So the log of 1 is always 0, so that's what this says. The logarithm, whatever the base is, if you take the exponential base, they're going to cancel. Here, take the log base 5 of 5x, the 5 and the log will cancel. Because this is log base 5 of 5 to the x, means 5 raised to what power is 5 to the x? Well, it's just x, so the log and the base cancel. So it's saying that the logarithm and exponent cancel each other. Also, when you take the logarithm of two things multiplied, you can rewrite it as a log of the first plus a log of the second. When you take a logarithm of two things divided, you can take the log of the first of the top minus the log of the bottom. If you take the logarithm of a number raised to a power, you can put the power out in front. These are called properties of logarithms, something probably from your past. Same thing as if they're subtracted, if they're on this side, you can squeeze them together and have the first guy on top, the second guy on the bottom, essentially 5 over y. If you're multiplying, you're adding, these numbers inside become multiplied. And if you have a number outside multiply, you can make it the power of the base, the power of the logarithm. And again, just a couple more things here. As I was mentioning earlier, logarithm means log 10. To solve an equation, to a logarithm equation, you essentially take the whatever base this is, you take the number, that number base, and you raise the logarithm. So you raise the 3, you take this thing and you raise it, You take the 3 and raise it to both sides. 3 raised to this, 3 raised to that. An exponential will cancel the logarithm because they're inverses. And so 3 to the second power is 9. You add 2 to both sides and you divide by 6. In this one, you have to actually, subtraction a little while ago, I kind of talked a little bit about it. Subtraction, you can put them together, and the first one you can divide by the second one. But now this is base of 10. In the previous one, log base of 3, we used the big 3 to cancel it. Log base of 10, we're going to use the big 10. 10 raised to that power, 10 raised to that power. This is going to cancel. So you have x over x plus 4. Any number to the negative 1 power means the reciprocal of it. So this is 1 over 10. So you crisscross them. 10x equals x plus 4. Subtract x from both sides. 9x equals 4. And then divide both sides by 9. So you get 4 9ths. Over here, to cancel an exponent, use a logarithm. To cancel a logarithm, use an exponent. So they kill each other. So here, log base 2 of both sides. So now because x equals log base 2 of 5, use the change of base formula. It says natural log of the 5 divided by natural log of the 2. And when you put in your calculator, hopefully I don't butcher this. I got that right there. 2.3219, and I usually go 4 decimal places. And problem number 4, as I mentioned a little while ago, natural log and e are enemies of each other. So whenever you're trying to cancel e from a problem, you're trying to get to the exponential, and the e is the base, take natural log of both sides. So you get 3 over 3x equals natural log of 6, divide both sides by 3, and then you just take natural log of 6, make sure you cover the 6 in parentheses, and then just divide it out. And that's what happens. And then so as you're doing this, as you're looking at a couple of problems with logarithms, a number of non-farm jobs in millions added to the U.S. economy by quarter can be approximated by the function f of x equals 12.1 plus 2.3 natural log of x, where x equals 1 corresponds to the first quarter of 2014. So it says, what is the approximate number of jobs in the third quarter? Well, if 1 is the first quarter, then 3 has to be the third quarter. Essentially, that makes sense. In 2016, quarter number 3. So you're looking for the third quarter in 2016. This is the first quarter of 2014. So essentially, 2014, there are 4 quarters. 2015, there are 4 quarters, 8 quarters. And so you're looking for the third quarter in 2016. That's the 11th quarter from 2014. So actually 11, plug it into the function. That's about 17 million jobs, more or less. That's pretty good. In what quarter will the number of jobs be approximately 16 million? That's the one where you let the function equal 16 and you solve for x. So you subtract 16 minus 12.1 is 3.9. And you divide both sides by 2.03. Now to cancel natural log, again, natural log's inverse is e. Now essentially to kill this guy, you're going to take e to both sides. And so e raised to this power is 6.83 roughly. So you have roughly about when x is 7, almost, it's kind of like, it's 6 point something. So that's like the 6th quarter has already passed. So you haven't quite, you haven't quite gone through the first 7th quarter yet. So it's almost like you're going to the 7th quarter. So it's almost when x is 7. So it's the second, it's debatable here. So it could probably be, if you want, the 2nd quarter or the 3rd quarter in 2015, because it's 6 and change, but it's not really into the 7th quarter yet. It's really into the 2nd quarter. So this is debatable, but I just put 3rd quarter just to approximate up. But I believe probably the 2nd quarter, because you're still in the 2nd quarter. That's when it happens. So roughly, that's just the kind of idea of what chapter 3 and chapter 4 hold for you, just for practice, just so you can have it. Hope this helps you in your work. So that's essentially the material for the first exam.